Peki bunlar 2000 ışık yılı uzaklıktaki kara delik sizin için iyi bir hedef ve daha iyi çalışmalar yapabilmek için bu konuda bir düşünceniz oldu.
Yeah, there's a even closer black hole, but still the mass is not gigantic. Yeah, it's so small that yeah, it comes back to whether we can do any stellar mass black. I mean, if we found one in the solar system, of course there is. Yes, then the scale would change. But otherwise, we're much better off looking at supermassive black holes further.
Yeah. Hocam, dünya dönmeye devam edince sen süper görüntülerle devam etmiştiniz. Dünya daha yavaş dönseydi veya daha hızlı dönseydi veya hiç dönmeseydi dediğiniz görüntünün çözümü değişir mi o zaman?
Tabii ki. If the Earth did not rotate, we could use the same. The only thing we could do would be to put telescopes on orbits around the Earth, and those like telescope orbits. If the Earth rotated more slowly, that would also be a problem, because it takes, like, some of those observations that I showed you are over 12 hours. So you look at different telescope pairs as the Earth rotates. Okay, now these two see it. Now these two see it. If it was much slower than that, then the source could have changed, and the atmosphere could have changed. So it would be more difficult to collect enough data from the same source state to use this interferometry technique. Faster, if the Earth rotated faster, I think that
The artifacts in this left image tells something about Earth, you mean oceans or continents somehow. Could this be digged out from?
I didn't mean it that way. I meant, you take the Earth, you put a telescope in every dry highland that you can find, every mountain, like Chile's Atacama Desert and Arizona's desert and Hawaii's volcano and South Pole and whatever. And even when you do all of that, it leaves large holes in your coverage of the Fourier space. So I just meant it's like we have to live with the oceans here.
But probably it tells something that we don't want to understand.
Yeah, that we can't do much more from the Earth. I think that's what it tells us. There's not much more, like, we're now working on a telescope in Africa, in Namibia. That's going to be useful, but there isn't much more to do from the Earth. I think that's what it's telling us.
So you said earlier that we didn't telescopes on Earth, like this part. We take the picture and put them together and we got not black hole. But the military was using telescopes that are outside of the Earth. But we have telescopes outside of the atmosphere right now. You said that they're not that much strong, but if we wear pictures together, wouldn't it be possible right now?
That's a great question. So, what's your name?
Rosha.
Rosha. Rosha is asking, if the next goal is to make an array of telescopes in space, why aren't we using existing ones that we already launched and they're operational? Why do we need to make new ones? Well, that comes back to the wavelength question. For example, JWST is a near-infrared telescope. Hubble is an optical telescope, some UV. You still need to make the dish and the instruments appropriate for the light that you want to see from this environment. So you would need to still make new ones that are observing somewhere around the millimeter waveband. It could be a little shorter if that's what we end up deciding on. But we can't use. First of all, their orbits aren't completely independent from each other. One is in a low Earth orbit, the other is in L2, the other is someplace else. So we would have to coordinate the orbits, and the second thing is we would have to choose the wavelength at which we want to make them. Okay. Is everybody okay to keep going a little bit longer? Because we can stop and have a meeting. So I already showed you a version of this image of the black hole, its horizon, where if I shoot a ray, it's going to end up inside. There is no way for it to, like, if it's inside of the 5 gravitational units, it's going to be inside. And then I said, there is a special location just outside of 5M, where if I shoot a tangential ray, you see how some of it is going to make a loop-to-loop, go all the way around. And a lot of them are going to, so if I'm seeing it here, what that means is that these rays have already picked up a lot of emission from here, added some more, so it became very bright here. And then just outside of that, gravitational bending of light rays is weaker, so it's not picking up as much. Okay? So now if I take this mathematical concept and embed it in an accretion flow, like the one I showed you before, right? It's kind of thick, like not a thin disk. It's like a torus. It's rotating around the black hole. What that means is that for the types of black holes like Sagittarius A star, like M31, like M87, and about 30 others in our neighborhood. What that means is that how light traverses, like how light goes through this accretion flow, and how much brightness it picks up on the way is going to determine the image. So actually, let me just make a roadmap. I'm going to talk about 2 things from this point onward. We said we want to do a test of general relativity. We said we want to use the size of the image and its thickness and its characteristics, like the hole in the middle, to say if this is in line with what general relativity is predicting. We need 2 things for that. One, we need to say if the theory was not general relativity, but an alternative to it, like the ones Yavuz works on, for example. What would this image look like? Would it be different? Because if it's the same in an alternative theory and in general relativity, then you haven't done a test, right? If both results would look the same, you can say, okay, this is in line with the predictions, but it's not, it doesn't have a discriminating power. The second thing that you need to do is measure how the bright ring that you see relates to the space-time properties that you don't see. That's called the calibration, right? Because all I can measure is the bright stuff. I want to infer the dark stuff. So how do I calibrate? So those are the 2 things that we did using a set of models that we Dimitrios and I and a collaborator built, which this image is from. So in a series of 2 papers, we explored alternatives to the Kerr metric. What if the space-time of the black hole is not Kerr, and we still have all of those accretion flows around them, and what would the image look like? So for reference, this is here an HD curve. This is a Johansson Celsius metric. This is a Kerr-Sen. These are all different alternatives. This is a boson star. As you can see, it doesn't even have a horizon. It is a star still. What its image would look like, a dilaton and a worm. Okay? So we said, assuming the same mass and the same flow characteristics, can we tell the difference? Well, what we found is that indeed, for example, between the Kersen and the analytic JP, for the same mass black hole, both the horizon and the ring are different sizes, right? This is not the same prediction as that, which is great. That's what we were hoping for. But the relationship between the bright ring and the hole and the bright ring and the size of the hole is the same. So the calibration is the same between the bright and the dark stuff, but the actual size is different, which is the perfect scenario. Okay, that's why we are able to use this as a discriminating tool. What did we do? We took the bright rings that we measured. The way we do it for the observations, we did the same from our large suite of simulations, that stamp collection. We said, okay, let's define the diameter of the bright part. Let's measure the diameter of the dark part from the theory itself. And let's define a calibration that is the image diameter or the shadow diameter. We're doing it for the observations, and we're doing it for all of these additions, like simulations per and non-per. And we're doing the exact same process so that that calibration can be applied everywhere. The very nice result is that when we did this calibration over the bright ring you see versus the shadow size you want to infer, we found it's very tightly constrained. So that difference is almost always 0.1, with some uncertainty. So we can take all our measurements, use this uncertainty to say, okay, that's the uncertainty in the shadow size, and then we can compare it with the black hole mass. So this is our measured diameter. This is our calibration factor that I just showed you. This is the prediction from general relativity given an angular size in gravitational units. This would be the angular size. And if it's general relativity, then it's 1. It's alpha times 6 squared with 3 times theta g. If it's not general relativity, this is our deviation parameter delta. Okay? So measurement on the left side, measurement of the black hole mass from stellar orbits that got the Nobel Prize 3 years ago, especially for Sagittarius A star. We know it extremely well. That goes on the right side. And let's measure how big delta is. And as you can see, delta is centered around 0. So far, with all our theoretical models and measurements and the space-times that we considered, what we're finding is that this band is the allowed band within general relativity because of unknown black hole spin. And this is basically all the combination of uncertainties that we folded in fall within, like the peak falls within that prediction. So far, we are not seeing the deviation from Einstein's prediction for black holes. We were hoping to start seeing maybe some kind of, because there is dark energy, because there is dark matter, because there are inconsistencies between the geometric theory of gravity and quantum mechanics at the small scale. We are genuinely hoping that there's going to be some clue from somewhere about how we need to change the theory. It's not there yet. So right now, we are finding consistency. Okay, I think I'm going to stop here. I was going to show you some machine learning techniques where we made the image better. But maybe we can do it on a one-on-one. But I'll just flash it for you. This is the 2019 result for M87. And this is our reanalyzed result that allows a better, smarter way of filling in those gaps that the oceans and lack of telescopes leave. And we call that machine learning technique TMO. So it's, as you can see, it is a sharper image, less fuzzy than this one in the beginning. And how we did it is use our suite of simulations to build a better analysis basis. We didn't make any assumptions about what the image should look like, but we said if it is a ring-like image, then this is a better way to fill in the missing information. And this is the newest image for the M87 platform. We're going to do the same for Sagittarius A star as well.
Can I ask you this?
Of course.
You are still training the images from the models, right?
Correct.
This is the problem.
It's not, because all you're doing is you're using the characteristics of images to find a new basis set to build any image out. So you're not saying my image has to look like this. You're finding a new orthonormal basis from which you can build images out of. And as long as you don't put information where you don't have data, and as long as you don't limit yourself to images having to look like what's in your training set, it's just like using any other, like using words to make new sentences. It's just our words are better. So that's the idea behind it. It's a new dictionary. But yeah, I mean, that's of course
If
very
you
valid
have more
question.
data,
Are you-
real data.
Yeah, are you baking in something with machine learning that is not in the data, but in this particular case, we can show that. Yeah,
Any other questions?
Have you ever made any calculation about the black hole entropy?
no, but there are people, of course, who work on black hole entropy. But you're not able to use the images for that.
The set of simulations you have made, I guess they're also resolving the questions about attraction dominated disks, adios, and all these. These are a spectrum of models, and maybe now you have a favorite model for the disk. I mean, so many simulations. The purpose was not that, but probably you have something to say about that.
Yeah, that's a very good point. Since you have all of the simulation library and so much unknown, do you now have a favorite model? In the set of PhD papers, we applied a set of tests about what we know about the data. How quickly does the source brightness vary? What is the image size? What is, etc. But it was a pretty crude way of doing it. So yes, in principle, you can ask yourself now, which of these models worked and which ones didn't? But because we're missing the kinetic physics from all of those models that keep the electrons, and because the types of constraints that we applied in the PhD papers were crude, I personally am not at a point where we can say, here is a better model. In a couple of years, I think we might get there by putting in more electron physics and doing this better, like more systematically. But there are certain members of the collaboration who will say, well, we already know more, like MAD models are preferred. It's a particular magnetic geometry. I personally don't.
And the point where the jet is launched, I mean, do you see the launching of the jets from the simulations, and then can you decide what physics is launching it, etc.?
Not yet, but that's certainly something that is a goal for the age. We should be able to, for example, I didn't talk at all about it, but we also have polarization maps, which are very interesting and useful as a diagnostic. So by the time you combine polarization, variability, image characteristics, I think we will be able to say more, but maybe in a little bit longer.
Those images required any imaging, or polarization was there and you just acquired them? How did you get this polarization maps you share?
So EHD reports in different polarization channels, so we have the polarization data, but we have to analyze it. Instead of photo intensity, we have to analyze polarized light, and we have to compare it to models that kept track of polarization. Everything that I showed you here was total intensity. So in order to infer physical characteristics, we have to compare to models that follow polarization, which is what we did in subsequent years.
Thank you.
Any other questions?
Also, we could sort of compare the simulated images with known parameters and the sculpted images to infer some physical property of the object.
Yeah, I didn't hear the beginning. Can you start the question again?
Is it possible to sort of compare simulated images with known parameters and the sculpted images to infer some physical properties about the object?
Yes, and that's related to what Yavuz was asking too. So there are physical parameters that belong to the black hole, like mass and spin and space-time characteristics. And there are physical characteristics that belong to the accretion flow. Like, what is the magnetic field? How does it evolve? How does the plasma heat? Why do outflows and jets form? So far, I feel like we've done a better job of the first part, which is inferring the black hole characteristics. And we're just now beginning to make more sense of, let's compare our data to our set of simulations and understand more of the accretion physics. Certainly, there's a lot of ongoing work, but no final results in my view.
So we know the magnetic field intensity there, I mean, did you measure it now?
Magnetic field intensity is
Something.
easier to get, just the overall intensity, because what we're seeing here is all synchrotron radiation. So you can infer the combination of density, magnetic field, and temperature.
You need to know the energy of the reactants.
Yeah, we roughly know the temperature. Yeah.
I have a really question. It's a bit of off topic, but
How off topic, aliens?
not
Okay.
black holes.
Oh, yeah.
What are the connections between the team we call singularity, parallel universe, anti-universe, white hole, black hole, and Einstein-Rosen bridge? And if any of these stories wrong, how will the others be affected, and how will our perspective on the universe change?
I can't answer it in its whole generality, but what I can show you is this slide.
So a warm-up.
Yeah, where we are exploring alternatives to, this is a black hole that is described by a Churchill or a Kerr-Metric. Like, what if it was some other object with a different space-time? What would its image look like? So that we are definitely doing. As you can see, this doesn't have a horizon, it's a neutron star. This is a wormhole. It's one of the things that we listed. It doesn't get into okay, if there is a parallel universe with a different, metric, how does that affect black hole formation here? Like, those connections we are unable to make. But if there is a proposed alternative to GR, and we have the metric or whatever, last object that it's predicting, then we can say, okay, let's go ahead and look at what the image would look like and compare to what we're seeing. So that part.
Teşekkür ederim. Dersiniz devam ederiz sonra.
Bonus var, I mean, that's.
I think so, but.
Hocam. Çıkın hocam. Buyurun.